with this. This is the start of electrochemistry. So all of this is focused on a transfer of electrons. Now, almost all reactions have a transfer of electrons. Not all, but almost all of them. Again, movement of electrons. Movement of electrons. Okay, electrons have what type of charge?
Positive.
No, they have a negative charge. So when we talk about losing an electron, we're minusing a minus charge. We become more positive. If we talk about gaining electrons, we are adding a negative, so our charges become more negative. Okay, keep that in mind. Again, I always have to think opposites. Okay, so going through this electron transfer in a chemical reaction, we refer to this as a redox reaction. Again, it's a reaction where electrons are transferred. The full name of this we call an oxidation reduction reaction. I'm going to refer to this as a redox reaction. Okay, it's all about the transfer of electrons. Questions? Okay. Now, this stuff is very useful, right? Some of the things in this class are really abstract, very, very useful. I'm going to point out one example here, and that's hydrogen peroxide. So if you've probably gotten a cut on your hand or if you had a scar, your parents or somebody or the nurse is going to say, hey, put some hydrogen peroxide. It stings, it kind of has the bubbles, but it's preventing infection, which would be even worse for you here. So there are quite a bit of applications. Okay. Now, here we go with some terminology. Oxidation is loss of electrons. If we lose electrons, we are minusing an electron with a negative charge. We're minusing a minus charge. The charge itself becomes more positive. Oxidation, overall charge more positive. But we are losing electrons. Reduction, we are gaining electrons. We're adding electrons. We get a more negative charge. Now, a simple acronym that they've developed or we've come up with over the years is this. We call this acronym oil rig. So oil. I start with this, oil. Oxidation is loss of electrons. R, again, oil, and then you have rig. Rig, reduction is gain of electrons.
Why did that U just change colors?
Oh, I have it set it different. Hey, the thing you have to remember about this acronym is that electrons have a negative charge. So when we talk about the overall change in charge, we got to refer to what I've written here on the whiteboard. Okay? Questions? Does anybody need this? Again, oil rig. Yeah.
Plus, minus, or negative charge.
Okay, so we move on here, and we get to this. All right, take time, read it. You got it memorized?
Oh,
Hold on.
Just kidding. You do not need to memorize this. This is why I printed it out on a separate sheet of paper. You get to utilize this on the test. Now, oxidation number, simply put, is just talking about the charge. Okay? 3 points I want to make here. Remember, the charge in general, we can look on the periodic table and we can identify the charge. I'm going to show you that here in a second, or remind you of that in a second. Point 1 is right here with subpoint A. If you see something that is O2, Cl2, H2, N2, or S8, it gets a charge of 0. So you see any of those, charge is 0. The other thing I want to point out is this. Point E. If we see an oxygen, we're going to start there because oxygen gets a -2 charge unless it's combined or it's in the formula H2O2. At that point, it gets only a -1 charge. But we're going to start here. It's a very rare time that we see it involved, at least in this class, with H2O2. And then the final thing that I want to make is point B. Oxidation number, single element equal to the charge. Now, I didn't put this in here. I wish I did. But remember, if we looked at the group, we can identify the charge of that element. So in general, what point B is saying is that anything in group 1, hydrogen down to francium, gets a +1 charge. Group 2, beryllium down to radium, +2 charge. We skip over, we go to the group with boron, +3 charge. Carbon gets a plus or -4, and then we just start going back downhill. Nitrogen gets a -3 charge. Oxygen's group -2, -1, and then our noble gases 0. Remember, they have that perfect electron configuration. In general, this is where you're going to find the oxidation states of most elements. Now, some of the things kind of have some weird exceptions. In general, you're going to find a lot of the charges, or you can start at least here. Questions? Does anybody need this?
Wait, is this in for a survey?
What about the?
No,
what
South
about the bottom?
Dakota
The
State
middle one?
University. That is fine.
Do the
Oh,
middle ones have the number?
So the middle ones are unique. Remember, they're transition metals, and so they can have multiple positive charges. So example is this: copper can have a +1 charge, and it can pretty easily have a +2 charge. It can also have some other charges, but it's because they have multiple, we're not going to assign it this particular fact. Okay? So we're going to have to combine those rules with the stuff that we've talked about, and we get to our examples. All right? So our first example is this: potassium chlorate. The hardest part is figuring out, well, where do these things split? Well, I wrote this out, and they're going to split right down the middle. Now, potassium is what element?
Okay.
Very good. So in my compound, I'm going to do this. I'm going to split this. Then K, potassium, is in group 1. It was way on the left. What charge did we assign with that?
+1.
+1. So I'm going to make a little note. I'm going to say, all right, +1. And then I'm also going to do this. K4 potassium has a +1 charge. This means that chlorate, ClO3, this whole thing right here, it has to neutralize that +1 charge to get to a total charge of 0. So what does this, the entire chunk of ClO3 have to be?
-1.
Very good. The whole thing does. -1. Now, this essentially becomes a very simple algebra problem. So I'm going to start backwards because the overall charge of this whole compound is -1. Now, I said, and this is especially true, start with oxygen if you see it in these types of scenarios. So oxygen here, it's not with H2O2, so it has to have what charge?
-1.
It has to have, not a -1,
-2.
-2, but we have how many of them?
3, so it's -3.
So we say 3 times a -2. -2 is its charge. We have 3 of them because of the O3. Then, for this scenario, we don't have a specialized rule of Cl, and so that means we have to go find the charge of Cl. So we say plus Cl. Now, we're going to consolidate this. So we have Cl. What is 3 times -2?
-6. -6.
-6. Very good. Yeah. So Cl -6 equals -1.
Would you add Add 6.
Too easy. We add that 6. So we add 6, add 6.
CL equals 5.
Cl has a positive 5 charge. And I like to put this just so I know I've done it, is that oxygen has a -2 charge. All right? So we've identified the oxidation numbers of every single element in that compound. Let's move on to the sulfite ion. What's nice about this? Yes. SO3, it only has 2 different elements. So we split it right down between element 1 and element 2. Again, what's nice about this is we see the overall charge is already given. So we're going to start our equation with this. The overall charge is -2. If we see oxygen, no,
2.
it's -2. -2 charge, again, how many oxygens do we see?
3.
So we say 3 times 2. Then we have S. So we say, I don't know, sulfur.
-6 plus 6.
Yep, this consolidates to S -6 equals -2. We add 6 to both sides. And so what's the charge of sulfur here?
-8.
No. 4. Oxygen has a charge still of -2. Okay? So again, these are the oxidation numbers. These are the charges of every single element involved in these 2 example compounds. Questions?
Question. Why do I keep saying -1 for oxygen? Isn't that for H2?
Yeah, only if oxygen is in H2O2, then the oxygen's only -1. You're probably saying that because I emphasized that. Every other time you see oxygen, -2. All right? Does anybody still need this?
Wait, if every time you see oxygen, it's -2. Why put oxygen
The overall, this ClO3, the whole thing is negative.
I'm not taking that.
Oxygen contributes to that negative discharge. Good question. All right, so moving on here. Now, we're going to see this example again, so keep this in the back of your mind because we're going to use it towards the end. What's nice about this, we're going to go pretty quick here because we just went through examples. If I split K and BR, first off, K is in group 1.
So it's -1 or +1.
Okay, very good, +1.
So there's 2.
BR, and the coefficient doesn't affect things here. The VR is way on group 17, the last thing that I put a number with. So it's a, there you go, -1. Now, Cl2 is that special circumstance. Cl2, it's in its natural state, we call it, charge is 0. We then get to KCl again. Or if we get to K and Cl. K on the left-hand side, what is it? +1. Cl minus, way on the right. -1 there. And then Br2 is once more a special circumstance. It's 0. It's that first rule that was listed. Okay? So everything that we just took the time to go over, you guys did on your head in about 30 seconds. Okay? Keep this in mind because we're going to copy and paste this on an example here at the end. Yeah. Yeah, this kind of sets us up for the end of this section and really the whole chapter. Yep. Which one? Oh, Cl2 and Br2? Yeah, so they're considered an element in its natural state. So if it's in its natural state, it satisfies that octet rule of bonding. And so it does not want any more electrons. It's satisfied. And so that's why it's right at a charge of 0. Does that make sense? All right, so we move on to one more thing here, and that is this. Redox reactions. Why we have an electron transfer is all about the trends in electronegativity. Now, you don't need to memorize this, but why electrons go from one thing to another, are given off, or some things taken in, is all about this electronegativity chart. Now, I don't want to confuse you, but we throw two additional terms in here, and that is oxidizing and reducing agents. Let's simplify this. Oxidizing is the substance that allows oxidation to happen. It is the item that is reduced. Reducing agent is allowing a reduction to happen. It is the substance that gets oxidized. So, bottom line here, identify what is oxidized, what is reduced, and then you can slap these terms on here. So, our last two examples, this one looks pretty familiar because we just established the charge. So first thing to figure out, we need to figure out the oxidation numbers for each of these things. Now Br had a what? Very good. It had a -1 charge. Cl2 had a very good 0. In KCl, the K still has a what? Very good. And then the Cl has a, yep. And then our Br2, very good. Okay. So the first thing that we're going to do is we're just going to go step by step and figure out, hey, does this thing has a change from left to right in its charge? So potassium, K, +1 on the right, also +1. Anything happen there? No, so we don't worry about it. Br now goes from -1 to 0. So, did it get more negative or get more positive? More positive is associated with K. So, I'm going to put this. Our Br is oxidized because the charge gets more positive. Now, if it's oxidized, there you go, very good. It is the reducing agent, yes. Okay, now I'm going to walk through this. If you've identified one thing, you can identify the other thing pretty easily. Now, Cl2, if we take a look at it, goes from 0 to a charge of -1. Did it get more negative or more positive? Go for it.
It's the oxidizing agent.
Why is it oxidized, but then it's not the oxidizing agent?
Because it's opposite.
So it is allowing for the other substance to be reduced. That's why it's called the reducing agent, but the substance itself is oxidized.
Oh.
I think opposites.
I read A on both of them, and then I was confused, but then I read B, and then it made sense.
Gotcha. All right. So Dylan said this thing gets more negative, which means our Cl is reduced, which means it's what type of agent? Very good. All right. Now we move on to our final example. Okay, I2O5 is a compound. Now we got to pause here. We can't start with I. We got to start with oxygen. Oxygen always has a charge of what?
-1.
Not -1.
No, -2.
-2, unless it's one of the exceptions there. Okay? Now, let's think to ourselves, because we got to do a little bit of work. Iodine has to balance this charge out. If we have a -2 charge times 5, what's the overall negative charge from oxygen? -10. So think to yourself, what times 2 equals -10? Not positive 5. Positive 5. If you have something that's negative, you're going to have something that's positive in that. So
Choose positive.
-2 times 5, -10. We have to cancel out the charges. That's the term I should have used. Cancel out. So that makes sense why it's a positive 5. Okay. So we got a positive 5. Okay. Then Carbon splits from oxygen and carbon monoxide. Again, start with oxygen. What charge is it?
-2.
Very good, -2. Okay. Carbon has to counter or has to cancel that -2 charge. There's only one of them, so it has to be positive. What? +2. Okay. I'm going to say carbon +2. And then iodine, special circumstance, so a charge of,
0.
very good, charge of 0. And then we do the same thing with CO2. Split it down the middle. We know the charge of oxygen in a compound is what? -2. Now, it has to cancel out. We have -2 times 2, which is -4. Carbon has to cancel that out, so it's what? Positive 4. Okay? So, on this here, let's walk through it. Iodine, I goes from a +5 to a 0.
It's getting more positive, so it's the.
Is it +5 to a 0?
Oh, no, it's.
Negative.
Oh,
It's getting more negative, so it's reduced. So, our iodine there is our reduction there. It's where our reduced portion happens, and it is, like you guys said, oxidizing agent. Now, oxygen, in both cases, and actually all three cases, it is always in -2 charge. So check, don't worry about it. Okay? Then,
Even if there's 2 on one side?
correct, because we're just looking at the charge if we just take away all other factors. Carbon, we have a +2 charge on the left, +4 on the right. Does it get more positive or more negative?
More positive.
More positive, which means it's what?
Oxidized.
Yes, very good. So we say that our carbon is oxidized, and what type of agent is it?
Reducing.
Very good. All right, any questions?
So
You
we're
two already got
not
my
gonna take a
test.
test over 20, we're just gonna do it on the final, right?
I'm pretty sure.
Yes.
Okay.